In this video we're going to look at the alternative derivation of the Jacobi Accessory equation. Now this is a little bit more intuitively obvious and I think you'll learn more from this derivation. So again, let's start by looking at an example in calculus. So let's say we were looking to find the second derivative of a function. So we've got a function here, f of x. We can find the rate of change of the function at point x1, so it's going to be df by dx at x1. We can find the rate of change of the function at x2, that's going to be df by dx at x2. Then we can find the second derivative, so this is going to be the rate of change of this rate of change. So if you like, you can think about it in terms of the curve being a very shallow curve or being a very steep curve. So if the curve is very shallow, then the rate of change of the rate of change will be low. But if the curve is very, very steep, then the rate of change of the gradient will be large. So that would really tell us about the curvature of the curve. So in order to find this second derivative, you can take the df by dx at x2, take away df by dx at x1 and divide it by delta x and take a limit as delta x tends towards 0. So this would be the delta x here, which would be the x2 minus x1. So that's going to be the same as df of x1 plus delta x minus df of x all upon delta x, and it's the limit as delta x tends to 0. So that's going to give us the second derivative, d squared f by dx squared. So there's nothing new in that, it's just the statement of the second derivative of a function. Now we want to do a similar thing, but we want to do the same sort of thing, but not with a function, with a functional. So let's say, for example, we have a curve here, f of x. Then we could put our thumb in this point in the curve, and we can move it to this point here. In which case the gradient, the position is going to change and the gradient is going to change from one side to another side. And we could write the Euler Lagrange equation for this. And it's going to be partial f by partial, say we'll call it y1, minus d by dx partial f by partial y1 derivative. Now we can take this point here and we can then shift the curve to another point. So in effect we're adding one variation on and then we're adding a second variation. So we could call this second variation, or we could work out the second variation again using the Euler Lagrange. So we could have an Euler Lagrange for this second variation that we put in. So that would be partial f by partial y2 minus d by dx partial f by partial y2 derivative. So this has us got the Euler Lagrange for the two positions. So in effect, having a position here and then having a position here and having the change in position, which is this little distance here, this is analogous to the simple function example where we have a position x1 and a position x2 and a distance between them of the delta x. But now we're not adding on this distance here, we're adding on a variation in the y direction. So in order to work out the rate of change of all of these changes, we can apply the simple form for our differentiation to the actual Euler Lagrange equations. So we could say the Euler Lagrange for position y2, which would be the bottom one, minus the Euler Lagrange for position y1, which was the top one, all upon the distance delta y. So this distance delta y would be this small distance here. And we could take the limit as delta y tends towards 0. So if we can work out this, then we would be working out the second derivative of the Euler Lagrange equation, which would give us our Jacobi accessory equation. So let's go ahead and we'll see if we can actually work through this here. Now I've rewritten the equation we're interested in here at the top of the page. Now a thing to note here is that this only gives us a localized variation. It's only at one point, but remember, whenever we are working through the variation of a functional, it's over a particular region of that function, so from some point A to some point B. So what we said is in order to use the analytic method over the entire range of the function, we think about having a curve eta x. So this is a curve eta x in yellow. We can then multiply that curve eta x with some value epsilon. So this is going to give us a family of curves. So the yellow curves here we see are the eta x epsilon curves. We can then take the function y of x and we can add on this variation to the function. So this would give us the y1, which would be our y of x, which is our original extremum, plus the epsilon eta of x. So this would be our original extremum, and the yellow one would be original extremum plus some variation. But then what we're going to do here is we're not just going to add on one family of curves, we're going to add on a second family of curves. So the second family of curves is going to be given by the u of x. So the u of x is some other function, so I've drawn the u of x out in blue. And we can take the u of x and multiply it by some factor epsilon, and this is going to give us a family of curves in blue here, which is epsilon u of x. And we can then add this variation onto the y of x, and we would get y2 of x equals y of x plus epsilon u of x. So in effect, what we have here is a method of adding on two different variations. So this is similar to the simple example where we pick a point x1 and then pick in to find the gradient, and then pick a new point x2 to find the gradient. Or equivalently, in terms of the Euler Lagrange, we have the Euler Lagrange for one point and Euler Lagrange for another point. So now, in order to get those two different points, we're adding on two different variations. So what we want to do is we want to take account of this within this equation here. So let's go ahead and we'll add this into this equation here. So we're going to have the limit as epsilon tends towards 0, because epsilon is the only thing that is going to control the variation. So it's going to be your partial f by partial y of our functional. So our functional is going to be given by x, y2 derivative. Okay, so this is the second addition of a variation, which is this one here, minus d by dx of partial f by partial y derivative, which is just this point, over function partial f. Well, it's going to again be a function given by x, y2 derivative. So in effect, this part here is this part of it here, where we've noted that the actual function is written in terms of our original extremum plus a variation. And then we're going to take away the second part here, which is going to be our partial f by partial y of x, y1 dash, and our d by dx of partial f by partial y dash f of x, y1 y1 dash. So now what we can do is we can actually rewrite this again, and instead of the y2 and y2 dash, we can actually put in the actual dependence on our x. So the dependence on our x for this one up here is going to be our partial f by partial f of x, and we would have y plus, and for this one it's going to be our epsilon u, so that's our epsilon u here, plus y dash plus epsilon u dash, and the same for the y2 and y2 dash here. And again we can replace this y1 and y1 dash with our equivalent here, which is going to be our y plus epsilon eta and y dash plus epsilon eta dash. Now you can see here, I think there's a slight mistake in this here, because the minus sign here should just be outside the bracket. You can see this minus sign here, it should be outside the bracket here. So whenever we multiply that minus, this would become a minus and this here would become a positive. Okay, I'll make a change in that in the notes. So now we want to work through this here, and we want to do the differentiation and then get it in the form of the Euler, the Jacobi accessory equation. So let's go ahead and we'll do that in the next page. So I've just rewritten the equation up here. I've actually written it correctly this time. I've taken the minus at this point here. So if we're going to differentiate this here, we're going to end up with second derivatives and mixed derivatives. So let's take the first term here. The first term here, we're going to have our partial squared f by partial y squared. And whenever we differentiate the term here, if I just write this down, we're going to have our y plus epsilon u is differentiated with respect to our epsilon. So we would end up with our, it would be our partial. Now the y is not a function of epsilon, y is a function of x. Okay, so y of x is our extremum, and it's nothing to do with the value of our epsilon. So this second term here, epsilon u of x, so we're going to have partial epsilon u by partial epsilon. Now we've got a product of two functions here, so there's the epsilon and there's the u, so that's going to be our partial epsilon by partial epsilon times the u, plus, if we'll go partial u by partial epsilon times the value of our epsilon. Okay, so that's just the product rule for differentiation. We differentiate this one and then multiply it by this one, and then we differentiate this one here and multiply it by this one. But now note that partial epsilon by partial epsilon is a value of 1, so that's just 1 times u, which is a value of u. Now this partial u by partial epsilon is going to be 0 because u of x is not a function. U is not a function of epsilon, u is a function of x. So we choose one value for one family of curves, u of x, and it's nothing to do with the epsilon. So we're just going to end up with that term u here. So this term u here is this term u here. Now the second one here, we're going to have partial squared f, and it's going to be the mixed derivative. We're going to have our partial y and our partial y derivative here. And again, whenever we do the differentiation here, it's the same as this. So we just end up with, in this case, the u derivative. And we've got the next term here, which is our d by dx. So we're going to minus d by dx over partial squared f, and we're going to have our partial y derivative, that's the mixed derivative, times our u, and finally we're going to have our partial squared f, we'll have our partial y derivative squared times our u derivative. So this here is the differentiation of what we have above here. Now a nice little exercise to make sure you understand that is to work from this here and work our way back and see if you can take this equation, and given that you know the dependence here already, y plus epsilon u of x and y derivative plus epsilon u of x, and also the e to x and the e to x here, we can take this and rewrite it back in this format here. It's a good exercise. So what we're going to do is we're going to take this here and we're going to generate the Jacobi accessory equation from it. So we'll leave this term as is, so that's the term here, and we'll leave this term here the same as we've got here. Now what we're going to do is we'll do the differentiation on this term here. Okay, so this here is going to be a product of two functions. So that's one function here, and there's the other function which is the u. So we're going to differentiate our u with respect to x. That's just going to give us our u derivative, and then we'll multiply it with what's left over, and that's what's left over here. And then we're going to differentiate we're going to leave the u as it is, and we'll differentiate what is left over. So what's left over, and we just leave it as the differential d by dx of this here. Okay, I've put delta there, that should be partial. So that should be partial. Okay. And we'll just leave the final term as it was previously. So it's minus d by dx of this term here. So we've got 1, 2, 3, 4, 5 terms. And you'll note the reason why we did that is because this term here is exactly the same as this term here. Only one's positive and one's negative. So it means that this term and this term can cancel out. So we can scrub that out and we can scrub that out. And we're going to be left with these three terms here. So the three terms are going to be our u partial squared f by partial y squared. And we've got our this term here, which is this term. And we've got this term here, which is this term. So now if we were to replace the partial squared f by partial y squared with our simplified nomenclature, that would just be u f00, and then this one here would become u minus u d by dx f01, and this one is minus d by dx f11, which is this one, times u derivative. So now if we take out the common factor here of our u, then we're left with our Jacobi accessory equation, which is our u times f00 minus d by dx f01 all minus d by dx f11 u derivative, and that is equal to 0. So this is our Jacobi accessory equation, and it's been derived in a more geometric fashion. And the beauty of doing this is that we're able to, if we go back to a previous page, we're able to relate the two functions now, our eta of x and our u of x. And we can see that our eta of x and u of x are two different families of curves that introduce the two variations. And we're taking in effect the limit as these variations tend towards one another. So that's us got the two equations that we require. We've got the Jacobi accessory equation, and we've also got the second variation, which we derived a couple of videos ago. So in the next video, we'll take those two equations and we'll go through a proof of the Legendre test for weak extremum, which we simply stated in a previous video. So thank you for listening. I'll get you on the next video. Goodbye.